My full topic is electrostatic force, Coulomb's law, charges, Millikan's oil drop experiment, electric fields, point charges, and parallel plates. Electrostatic force. Electrostatic forces are non-contact forces. They pull or push on objects without touching them. Rubbing some materials together can result in something called a charge being moved from one surface to the other. So this is the formula and constant for electrostatic force. So electrostatic force equals K, and the constant is 8.99 times 10 to the power of 9 newtons times meter squared divided by coulomb squared. So these are basic definitions that correspond to electrostatic force. So as seen in the formula, electrostatic force is proportional to both Q1 and Q2 in the formula. Repulsion attraction is like charges repel and unlike charges attract. Inverse square law is the forces between two charges is directly proportional to the product of their magnitudes and inversely proportional to the square of the distance between them. Distribution. Charges reside on the external surface of conductors and equally throughout non-conductors. Concentration is the greatest concentration of charge, and movement is only negative charges move along solid conductors. So an example problem for electrostatic forces: when distance increases, electrostatic force blank. We call this relationship blank proportional. So the answer here is 2. This is because in the formula, the distance is dividing the charge, which causes the electrostatic force to decrease the bigger the distance between the charges. That's what makes this an inverse relationship. Coulomb's law. Coulomb's law states that the electrical force between two charged objects is directly proportional to the product of the quantity of the charge on the object and inversely proportional to the square of the separation distance between the two objects. This is basically stating that the Coulomb's law describes the strength of the electrostatic force, whether that be attraction or repulsion, between two charged objects. So understand that these are two key points that come from Coulomb's law. The electrostatic force between two objects is directly proportional to their charge and inversely proportional to the square of the distance between them. This is also seen in the formula as distance is squared. So the equation is the same as the electrostatic force, and the equation can still be modified depending on what the question asks for. This equation corresponds on page 4 of our yellow reference sheet. So an example problem for Coulomb's law is if the distance separating an electron and a proton is halved, the magnitude of the electrostatic force between these charged particles will be. The answer here is 4. The answer is 4 since the distance is inversely proportional to the charge, which means that since the distance is half as much as the charge is each pretty much doubled, which makes the electrostatic force be quadrupled. Charges. There are two types of charges. There are positive and negative charges. Protons are positively charged and electrons are negatively charged. If an object has more protons than electrons, then the net charge on the object is positive. If there are more electrons than protons, then the net charge on the object is negative. So transfer charges. There's conductors and insulators. Conductors do not hold on to charges well and have high conductivity. Insulators are good at holding on to charges and have high resistivity. So in these pictures, you can see that some good examples for conductors and insulators. They both are different materials, but conductors lean more towards different metals. So these are electroscopes. This picture shows what the electroscope is, and when an electroscope is charged, the leads will repel each other and open up, and when it's uncharged, they will close up. The electroscope is a piece of equipment that is used to detect the different charges. So induction, that basically means no touching. So as you can see, induction is generating electrical current without touching the charged rod or the electroscope. In induction, a different substance will give opposite charges to the rod, meaning a positive rod will give a negative charge and a negative rod will give a positive charge since they're opposite charges. Conduction, it means they're allowed to touch. As you can see, conduction is generating electrical current while touching the charged rod. In conduction, it creates the same type of charge that the rod gives off. Meaning, if a positively charged substance touches the rod, it'll give a positive charge to the rod. Millikan's oil drop experiment. So the aim of the experiment was to find an accepted value of the electron charge, which is what we know as negative 1.6 times 10 to the negative 19. So these are the products used in this experiment, which was a perfume bottle, very fine oil, metal plates, a battery, and a microscope. So he uses oil instead of water since oil won't evaporate during the experiment. And in the experiment, he drilled holes in the couple sheets of metal and connected batteries so he would change the voltage of the plates. He then used a microscope so he could see the drops fall, which did immediately end up working. So for the explanation of this experiment, the idea was that the oil was sprayed so it could pick up some amount of charge. He found the mass of the drop from a measure of its diameter, and the oil's density. Then, with the electric field's strength, he calculated the drop charges. Electric fields. Electric fields exist in the area near charged objects. Formula for electric field. So this is E equals F divided by Q. E is electric field strength, which is newtons divided by coulombs. F is force, which is newtons. Q is charge, which is coulombs. And this is on reference page 4 of our reference sheet. So this formula can also change depending on what the question is asking to find. The force is in between, the charge is in coulombs. The force is in newtons, the charge is in coulombs, and the electric field strength is in newtons over coulombs, which we stated before. So this is a quick fact about electric fields, that an electric field strength is a vector that is inversely proportional to distance from a charged object. So this is an example problem. A small charge, the charge is 6 millicoulombs, is found in a uniform electric field, which is electric field strength is 2.9 newtons per coulombs. So determine the force on the charge. So first you have to convert the millicoulombs, and then you do that and you get 6 times 10 to the negative third, and then you times that by the electric field strength force, and you get the 0.02 newtons as the answer. Electric field diagrams. So this is the positive and negative charge electron field. So the positive arrows always point away from the center, and in the negative charge, the arrows point towards the center. A key point is that when it's a single field, the lines do not curve at all. These lines are not curving. So this is a diagram of the negative and positive electric field when they are curved lines and the lines are still pointed toward the negative and away from the positive. These are two oppositely charged electric fields that are combined together, which is why they share the middle. So this is a double positive electric field diagram where we can see that the lines curve and they are repelling each other in the middle due to the same sign theory, which is why there's a big gap in the middle. So as we can see in this diagram, the double negatives are also repelling each other, and the arrows are still pointed towards the center of the negative. The direction of the arrows don't change from negative to positive. So when it's a negative, it's always going to be pointed towards the middle, and when it's positive, it's always going to be pointed away from the middle. But if it's a negative, it's still going to repel each other. So they're the same. They're equal forces, the same force. So point charges and parallel plates. So point charges this is a charge that has no area and no volume, but it can affect how an electric field will act towards it. It still applies under the rules that opposites attract and equals repel, like seen in the pictures. And a practice problem that would show the point charge would be set up like this, and you would have to draw the arrows on the negative charge, since the negative charge is being affected by the invisible positive charge, which is the point charge. So parallel plates. Parallel plates are a charged object placed between parallel plates will accelerate towards the oppositely charged plate at a constant rate. This picture shows it at a great example, as it's two plates with a charge in the middle, and they're both parallel from each other, one being positive and one being negatively charged. The arrows are always pointing towards the negative plate, and parallel plates are an example of when the electric field strength is in uniform. So if an electron was for example, if an electron was placed in the middle of the two oppositely charged plates in the parallel plate, the electron will move towards the positively charged plate at a constant rate due to it being the opposite charge, since the electron is negatively charged. The diagram does a great job of showing this because the arrows are moving from the positive to negatively charged plate, which does not change. To summarize, parallel plates are an example of an electric field strength in uniform, meaning it's still an electric field. Electric field. So an example problem I found was that an electron is traveling in an electric field as shown. Describe the electrostatic force acting on the electron while in the field. So we just talked about what happened to this. So the answer is C. The answer is C because the force is always constant in a uniform parallel field, and the electron will go in the opposite direction of its own charge.